All right, hello everyone. Today is June 1st. What my plans are is you do have a homework due tonight. Let me see which homework set that is. Just give me a second. Let me open my other computer for that. And I'll pull that open. Okay, so chapter 3 homework is due tonight. So the chapter 3 homework is due tonight. Does anyone have any questions for me? So the plan for today's lecture is to go into chapter 4. We'll do the chapter 4 PowerPoint notes today. We'll do the chapter 5 PowerPoint notes today. And then tomorrow, we'll work on the chapter 4 homework and chapter 5 homework tomorrow all at once. So that's my plan today. And then you'll see that the chapter 4 and chapter 5 homework is due on June 4th, which is a Saturday at 11:59 p.m. So that's the plan. You'll see that, we've kind of already had a chapter on nomenclature, but this one, that one was from Carty, and what the difference was, Carty has these inner chapters. We didn't talk about Newman projections, which is really important. So that's why you do have some homework set from chapter 4 from this one, because there are some problems that, you need to see that you didn't see from the other homework set. So that's why I went ahead and assigned a chapter 4 homework. You'll notice that it doesn't have as many problems to it. Let me see. I think it only has about 14 problems. I'm pulling it up right now. Yeah, it only has 14 problems. So we'll do chapter 4 and chapter 5 homework sets tomorrow. So let's go ahead and get started. We are going to start with chapter 4 PowerPoint notes. I'm going to go ahead and load that. And then we'll take a brief break between chapter 4 and chapter 5 note sets. Just make sure I'm recording. Yes, I am. All right, and some of this is going to be a brief review, but it's not a bad idea to have a review that has the talking points of nomenclature, since that's a large part of organic chemistry, is how to name the compounds. So alkanes, we have single bonds, and cycloalkanes, we have some type of ring structure. Something. So there was a question. Let me pull up the homework again. Oh, so let me see that. I don't see a tab either. Let me. Look at that. Okay, it should be there now. Can everyone see it?
Yes, it's there now. Thank you.
The tabs should be there in Blackboard now. It was in the Achieve assignment, but it wasn't in Blackboard, so the tabs are now there in Blackboard. And chapter 3 homework is what we did yesterday. All right. So chapter 4 is on alkanes and cycloalkanes. Just some type of cyclo compound, can be 3, it can't be 2, can be 4. So that kind of stuff. So hydrocarbons are composed of hydrogen and carbon. We have ethane, ethylene, acetylene, benzene. So what does it mean to be saturated? Saturated means no double bonds. And unsaturated means, we're going to have some type of double bonds or triple bonds or more than a single bond is what I'll say. Many organic compounds have common names, and they give you 4 examples. The IUPAC system is a systematic naming of compounds, and we saw this in the nomenclature chapter already. But we have the parent name, so if we have some type of long chain and then we have just something coming off, we're going to name the long chain first, and then we're going to come back to any substituents. Then the names of the substituents and the location. So we've kind of already seen this from our nomenclature chapter. So in this case, the parent chain has 1, 2, 3, and you just count. That's 9, so that would be nonane. And then you'd have, 3 methyl, and then you have, I guess you have 3 ethyl groups. So that'd be 4, 5, 6, triethyl. Remember the names, it has to come in alphabetical order. So ethyl comes before methyl, so you'd start with the ethyl groups first. So let's just say the parent chain has the same number of carbons, so let's just count them together. And I should have started from the opposite end on both of them, so let's do it the right way. So the reason why this is correct is because we have 3 substituents versus 2 substituents. So we chose the one with the most substituents attached, even though they both had 7. So we have methane, ethane, propane, and we've seen this before, but I think it's a good idea to see it again, all the way through decane. So it's 1 through 10. 1 through 10 for your carbon chains. Here we have, 11 through 100. Undecane, dodecane, tridecane, tetradecane, and hectane. So we didn't see this before, though. Do I have any questions so far? All right. Here we have the cycloalkanes. We have cyclopropane. We have a 3, 4, and a 5, right? All we did was add the prefix cyclo. So here you would just find the parent chain. Be hexane. It'd be cycloheptane. And then, the middle one, I'm just gonna go 7 that way. There we go. And we'll pick this one because that has the most number of constituents coming off. So naming substituents, practice example. So we have the parent, and then you have one here. This would be a methyl. Well, that's not a methyl group. Sorry about that. That's a ethyl group. So I need to erase that. There we go. That's a 2-carbon group. Here's a 3-carbon group, so that would be your propyl group. And this 1-carbon group would be your methyl group. And what is the parent chain here? Well, you count 1, 2, 3, 4, 5. It'd be 10. So 1, 2, 3, 4. Yep. So let's think about this. I'm gonna erase everything here. So there's 2 ways we can go with this 10 chain. We can either go, I'm gonna kind of draw this. We can either go that way, where we have a 4 position, we have a 5 position, we have a 7 position. Now we can go, let's try it the other way. We'll have a 4 position, a 6 position, and a 7 position. So with everything being equal, these are equal, but these are not equal. And we're going to pick the 5 because 5 comes before 6. So you go 4, 5, 7, or 4, 5, 7, yep. And sometimes I take my time right here because I know some of you are taking notes, so I don't want to go to the next slide. But if you ever want me to go back to a previous slide, just let me know. when they talk about this right here, and we spoke about it on the previous slide, where that first one coming off is an ethyl group, then followed by a propyl group, followed by a methyl group, and they've identified it for you. So I'll just let you look at it for a second. And note here, instead of ethane, this is ethyl. It's a YL. And that's because that's not the parent chain. It's just a substituent. So we can have, so a ring can be a parent chain or a substituent depending on the number of carbons. Here it has a larger number of carbons, right? We have 6 carbons versus 3. So that's why it's going to be the parent chain. Here we have 3 versus what? 1, 2, 3, 4. So the parent chain is just going to be the alkane, the linear alkane. So in the 1 position, you have cyclopropyl. This is cyclopropyl group, and this is 2, 3, 4 butane. This is cyclohexane, and we could draw this, it's still in the 1 position no matter where you put it. That's why you don't put a 1 right there. You could imagine you could just keep on rotating this down and it's still in the same position. So it says for substances with complex branches. So we have more than 1 branch off of this one. So 1, 2, 3, 4, 5, 6. So we both get 6. Going each way, it's both 11. It's an undecane. Number the longest carbon chain within the substituent. So within the substituent right here, we have a butyl group, 1, 2, 3, 4. And at the 2 position, we have a 2-methyl butyl. It says some branch substituents have common names, 2 types of propyl groups, and we had this in our homework set and the nomenclature. Right, this is the isopropyl group. This is the propyl group. Butyl has a few different types of butyl groups. You have the sec butyl group, the isobutyl group, and the tert butyl group. This is just something that, to be honest with you, you just have to memorize this. I don't like saying that, but it's the truth for this type of stuff. And you identify the sec butyl group, with how the carbons are coming off. I try to draw the carbons for you. And really, to be honest with you, the only way to really get to know all this stuff, just take out, if you have some type of computer pad, just keep on drawing them over and over again and just keep on labeling. You'll eventually get them. I mean, that's my best advice, just draw them over again. And, by repetition, you'll get them down. So here, now they talk about numbering. It says carbons in the parent chain have to be numbered. We kind of talked about how we're going to number them. We're not going to start on the right-hand side here. We're going to start on the left-hand side because we get to the 2 quicker. If we start on the right-hand side, we would go 1, 2, 3, 4. 2 is less than 4, so we're going to go with the 2. So we're going to go with the one with the lowest number first. And they show it to you right here. Number the parent chain so that citrulline has the lowest number possible, and that's what we did. In this case, it was a different molecule. That's why I have 2 versus 4. In this case, they have it at the 6 position, at the 2 position. So you're going to go with this one, the 2 position. So it says guidelines the following when numbering the parent chain. When multiple substituents are present, number the parent chain to give the first substituent the lowest number possible. And here we do. We put it in the 2 position versus the 3 position. If let's just say they were both 2, then you go here. Then you go to this position right there. So this might be 5, this might be 6. So 5 beats 6. So then you go at 2, 5 versus 2, 2, 6. And it says that right there. If there's a tie, then number the parent chain so that the second substituent gets a lower number. 3 is lower than 6 or 5. So you're going to go with this one right here. And that's due to this middle values. Then if there is no other tiebreaker, in this case, then assign the lowest number alphabetically. So B comes before C, so you're going to go with 1 bromo first. Oh. The same rule applies for cycloalkanes, so cycle groups. A 1,1 beats a 1,3,1 or 1,3,3. Does everyone see that? And there's 2 methyl groups in the 1 position, right? So that's why you got 1,1, and at the 3 position you have another methyl group. Here they're going from 1,3,3. They're saying the 2 methyl groups are in the 3 position, but 1 is lower than 3, so we're going to go with the 1 on the left hand side. If this doesn't make sense, just put something in the chat so I know. Okay, I got something in the chat. All right. Let me go ahead and erase this. So basically, we have the same molecule on the left and the right-hand side. And there are 3 methyl groups with each molecule. A methyl group is just a CH3 group. You know, we could draw the hydrogens coming off here, but you know, it's just implied that they're there. So we have to decide, you know, here, you know, we have 3 methyl groups, you know, so it'd be 1,1,3 trimethyl cyclohexane. But we have to decide, you know, what are we going to do? Are we going to put the, you know, are we going to go with this designator, or are we going to go with this one right here? With this one right here, we're saying that we have, you know, here's your hydrogens coming off here, and likewise it'd be right here. We're saying that, you know, we have one methyl group coming off here, right here. We have the second methyl group coming here, and the third methyl group is coming off right there. This one right here, we have one methyl group. Here's your second one. Here's your third one. So if we're just going to look at this right here, you know, the 1,1,3 versus the 1,3,3, you know, we start in the 1 position. So let's get rid of, I have a lot going on. So let's get rid of all that. So in the 1 position, we have this one, and here we're saying we have this one and here. And we also have another methyl group in the 3 position. So, okay, you know, 1 and 1, that's okay. You know, here we have 1 in the 1 position. And I'm going to go ahead and erase this again because there's a lot going on. Oh. Here we have 1 in the 1 position. We'll just count that one. Here we have this one right here. Now let's go to this one. Here we have that one. Here we have that one. So here we establish, you know, something's going to win. And here this is a 3 here, and this one would be the second 3. I mean, they're identical. I'm just putting that out there, you know, just to have something as a placeholder. So 1 and 1 is the same. Now we come right here and we have to decide, you know, what is the lower number? You know, so 1 is lower than 3. So you can think of it as a race. You always want to be number 1. You know, you don't want to be, you know, 2 or 3 in a race if possible, if you're running a track meet. So, you know, we're going to go with the 1 position here because, you know, a first place in a 100-meter is going to be better than a third place in a 100-meter. So that's why we're going to go with the 1,1,3 versus the 1,3,3. So you're always going to go with the one that has the lowest numbers. So you don't want to have the highest number. The highest numbers doesn't win in this case. All right, you're welcome. So to assemble the complete name, put the number and name of each constituent before the parent chain name in alphabetical order. Remember, we have to go alphabetical order. So if we have ethyl, you know, and let's just say we have, I don't know, methyl, butyl. So this one has ethyl group has 2 carbons, a methyl group has 1, and a butyl group has 4. Well, butyl, you know, alphabetically comes before E, because B comes before E, comes for M. So you're going to go butyl, then ethyl, then methyl. So you're going to go with alphabetical order. That's what they're saying right here. A prefix is used as di, tri, tetra, penta, etc. if multiple. So in the last example, we would have used tri because it's trimethyl. So even though we had different positions, you know, we had the 1, 1, 3, it would be trimethyl because there are 3 methyl groups. It says note, di, or tri is ignored when alphabetizing the substituents because there could be all kinds of substituents coming over, and we may have a penta, and it could be pentabutyl. Let's just, for instance, say we had pentabutyl, and then we had di, and you think, well, D comes before P, but we can't do that. We're going to go with the parent name. It's, or not the parent name, but the substituent chain name before we go to, and we don't even use the di or tri for alphabetizing or numbering. It says list the numbered substituents before the parent name in alphabetical order. And if you refer back to the nomenclature homework, that's a good example. We do go over some examples in nomenclature homework about assigning names and where they should go. And they give you an example right here too. So first you want to identify the parent name, and the parent is going to be 6, because if you count, there's only 4 here. There's only 2 here. There's only 1 here. So we have to go with the longest one. That's why we have hexane, and it's a cyclo group. So I'm going to go ahead and erase some of this stuff because it's getting busy here. If it loads correctly for me. There we go. So we established we're at a cyclohexane. Now we have to figure out, okay, what else do we have here? The only way that this is tert-butyl, you have to go back to the the common names of those butyl groups. Remember the common names. That's why I said some practice needs to be made. And here it is right here. So you have to go back and practice these butyl groups really to get down, which one's a sec-butyl versus an isobutyl versus a tert-butyl. This is pure memorization right here. I don't like saying that, but it is true in this case. So we identified that this is going to be a tert-butyl group here. We identified, we have an ethyl group and we have a methyl group. So we're going to start 1, 2, 3, 4. If we go the other way, we go 1, 2, 3, 4, 5, 6. If we went 1, 2, 3, 4, 5, then the numbers are too high, and going counterclockwise gets us the smaller numbers. So we have to identify which direction we're going to go, counterclockwise or clockwise. And we're going to go counterclockwise because we have the lowest numbers this way. I'm going to get my eraser out. I'm not going to erase everything this time. There we go. I want to get rid of all that. So we identify we're going counterclockwise. And at the 1 position, we have 2 methyl groups. And at the 3 position, we have an ethyl group, and at the 4 position, we have a tert-butyl group. So now we have to establish, okay, which one are we going to put in order? Well, B comes before E, comes before M, right? If you just think about the alphabet, B comes before E, comes before M. So that's Bravo, Echo, Mike. So you have 4 tert, and remember, these designators such as di, that doesn't matter in as far as who comes before what. So we have B, so we're going to go 4 tert-butyl, 3 ethyl, 1 1. Why do we say 1 1 right here? Because in the 1 position, you have an ethyl group, and in the same 1 position, you have another ethyl group. So it's 1 1 dimethyl cyclohexane. So I'm going to let you look at that for a minute. I just want you to study it yourself. So bicyclic compounds contain two fused rings, and so this is the same thing. So that's why it's good to have a molecular model set. This position right here is this top right here. You have 1, 2, 3, 4, 5. No, should be a 5 right there. 6. 1, 2, 3, 4. So everyone see the 6-membered cyclic ring? And all they did right here was they kind of rotated it this way. So it was a 90-degree rotation basically to show you this right here. So we call those the two carbons where the rings are fused. So we have a ring right here, right? And here's your cyclic ring right here. But where they're fused at, they're called bridgehead carbons. So these are called bridgehead carbons right here. And you have two bridgehead carbons, right? You have one right here, and you have another one right here. And this would obviously be the bridge right here. So there are 3 paths connecting the bridgeheads. Count the number of carbons in each path to name the compound. So these are 2 separate compounds right here. We're looking at 2 separate compounds. These are 2 separate compounds. I'm going to get my eraser out. It's getting a little busy. So we're looking at these 2 separate compounds right here. We see that there are 6-membered rings though, right? We see that, we have 6. I'm just going to count here, 4, 5, 6. That one has 6, 1, 2, 3, 4, 5, 6. So we have a 2 6-membered cyclo. It's 7. Let me see. Two 6-membered rings, but they're each bridged. That's how you get the heptane. Because that 7th carbon makes it the heptane right there. So I'm going to get rid of my get my eraser out. Erase everything. So how do we get, the question is, there are 3 paths connecting the bridgeheads. Count the number of carbons in each path to name the compound. So we've established that, yeah, we have 2 cyclic rings that have 6 carbons, but we do have that bridge with the 7th. That's how we get the heptane. Now, how do we separate them? Well, they're bicyclo compounds, and we're going to count the path to get to the there are 3 paths connecting the bridgehead, so we're going to count the number of carbons in each path to name. So in this path, we're going to go 1, 2, 3. If we go that way, we get to both bridgeheads, don't we? Here we only need 1 to get to the bridgehead, right? Or to the bridgehead carbons. Here we only need 1 right here to both get to the bridgeheads. That's how you get 311 heptane. So with this one, we're going to start with the largest number first. So you have 3 different paths to get to the bridgehead carbons. So you have one that has 3 carbons, one that has 1 carbon, and the other one that has 1 carbon. Here we have 1, 2 carbons to get to the bridgeheads. Here we have 1, 2. Here we have 1. So it'd be 2 carbons, and 1 carbon right here. So everyone see that? And this is something that this is just memorization too. So a lot of this naming unfortunately has more memorization than mechanisms. Mechanisms don't have as much memorization, but these do. It's just the way it is. You know, I don't really like when you just have to memorize something, but that's just the way it is for this, if I'm being honest. Any questions on this? Because this might be a little confusing right here. You know, you have 3 carbons, you know, to get to these bridgeheads. You only have 1 carbon to get to the other bridgeheads. And then here you have 1 carbon. Here you have 2 carbons, and 1 carbon. So that's how many carbons, you know, it takes to get to the bridgeheads. It's the path connecting the bridgeheads. And the reason why it's heptane and not because we have this bicyclo compound. So I know this might be a little confusing right here, but it's just, you know, it's one slide. The next slide doesn't even go on to this, but they just want to throw this out there. And this is on page 149 in the book too. Okay, I got something. So that's a good question. You know, the question is the bridgehead number always 1? And let me erase some of this stuff. It's getting a little busy. I'm gonna erase all of it. And so we're not really, you know, we're not really saying that this is 1 right here or this is 1 right here. What we're saying is how many carbons does it take, you know, number of carbons it takes for the path to get to bridgehead carbons. That's what we're really doing right here. So, you know, in this path we have 1, 2. If we just say that this is the starting point. If this is our starting point, how many carbons does it take to get to Z? You know, okay, it's going to take 1, 2, and it took 2 carbons to get to Z. Well, how many carbons does it take to get to X to Z in this position? Well, it just takes 1, you know. And how many carbons does it take to get to X to Z in the other way? Well, it takes 1, 2. So that's what we're doing right there. And that's how you get, okay, 2, 2, 1, you know, bicyclo 2, 2, 1 heptane. Here we can think about the same thing. If we just type this one, let's just do the same designator, X and Z. You know, it takes 1 carbon to go from X to Z here, 1 carbon to go from X to Z in this position. It takes 3 carbons to go to X to Z on the left-hand side over here. Now, if this was coming off, let's just say this was coming off some long chain thing right here. Now we'd have to have a designator to put where it comes off. So let's just say this is in the I don't know, you know, this is in the 5 position on this thing right here. So we'd first have to name the compound, you know, this, let's just call this you know, undecane. So at the 5 position, you know, we'd have this right here. So then you go 5 bicyclo 2, 2, 1 heptane undecane. So these designators are only telling you how many carbons it takes, you know, for the connecting the bridgeheads. And, you know, let me see, let me erase all this. No, that's not what I wanted to do. You know, you could have a connection here, you could have a connection here. You know, I'm just, for example, you know, you could have this one. You could have this one. It could connect wherever, you know, it could even, I'm not saying this is, it could even have some type of connection right there too. So isomers are different structures. They have the same molecular formula. And constitutional isomers have different connectivity of atoms. And these are just definitions, something that you have to memorize. So constitutional isomers, many isomers are possible. So as the number of carbon atoms increases, the number of constitutional isomers increases. It says be able to recognize different structures as being either being isomers or being the same compound. So in this instance, these the ones highlighted in green are the same compound. At the 3 position, you have a methyl group. At the 3 position, you have a methyl group. And, it just continues on. There's a 180-degree rotation along the C3-C4 bond would make it more obvious. These two compounds are the same. I showed you, how to count that. So it's 3-methylpentane. What they mean by that, at the 3-4 position is right here. If you rotate this right here, you're going to get this right here. And those bonds between the C3, C4, they can easily rotate since they are single bonds. Now, if it would be a double bond, it'd be locked in. But since it's a single bond, it's going to have easy access to be rotating. So this is the relative stability of isomeric alkanes. So relative stability of isomers can be determined by measuring the heat of combustion. So this means you'd have to go and do this experimentally. Here's some different industrial uses of petroleum fractions. C1 through C4 is used for natural gas. You can see C5 through C12 used for gasoline. I'm going to just keep it right here. I think this is a good time to take a break, to be honest with you. So let's go ahead and take a 10-minute break. We'll come back at 11:05. And just take your time, and I'll see you soon. Thank you.